Thank you. Could you hear me? Oh, thank you. I'd like to first thank the sorry, thank the organizers for this great opportunity to present my recent papers. I have moved to Uppsala University since last month. I'm sorry I couldn't be there. I planned to attend in person, but sadly, I haven't received my UK visa yet. So my talk is about is related to number theory and CFTs. To be honest, I don't know how or whether it's related to machine learning and black holes, but I hope some audience can recognize the connection and tell me. So these are based on three recent papers with Professor Kim-Young Lee, who is in the audience, and with Zhihao Duan, who will come to Quemery in London soon, and another number series, the Hao Wang in China. Right, so I think it's fair to say that 2D CFT has become a common knowledge for both theoretical physics and many areas in mathematics, to name a few. We often use it in string theory and condensed matter theory. So mathematics, it's related to finely algebras, vertex operator algebras, modular forms, and modular tensor categories. So the standard knowledge of CFT, 2D CFT, can be found in this famous big yellow book, which is also my one of my favorite book, or any string theory books, chapter 1 or chapter 2. So I think so what I would like to talk about is the simplest case in 2D CFT, that is the 2D rational CFTs. So the rational here means that there are a finite number of conformal primitives, and the central charge is rational, and all conformal widths are rational. So I think some audience may begin to wonder, hasn't the story of 2D rational CFTs already finished in 90s? So I hope from my talk, I can convince you that the story is not finished, and in fact, far from it. So in recent years, we are seeing a resurgence of interest in 2D rational CFTs. So among many progresses, there is this Hecke operator, which is the main topic of my talk today. So Hecke operator connects the characters of two rational CFTs. So if the characters of two rational CFTs can be connected by a Hecke operator, we will say that these two rational CFTs has a Hecke relation. So this Hecke operator was proposed by Harvey and his student Yu Wu in a few years ago. Yu Wu was also my classmate and a good friend. So they proposed this Hecke operator TP on a SL2Z vector valued modular form of width 0. This is a new Hecke operator, although mathematicians considered Hecke operator on vector valued modular form before, but somehow this new definition of Hecke operator didn't appear in previous math literatures. So the basic property of this new Hecke operator of Harvey Wu is it maps it depends on a parameter p, which is a positive integer, and it maps the central charge c to PC, and it maps all the conformal widths hi to phi, but it can be a modular integer. So in my previous paper with Zhihao Duan and Qiming Li last year, we systematically studied this Hecke of Harvey and Wu for many bosonic rational CFTs with up to 7 characters, and we found many new interesting Hecke relations. And later, we generalize this Harvey-Wu's Hecke operator to the fermionic cases. Mathematically, this is a Hecke operator on the so-called gamma theta vector valued modular forms of weight 0. So this gamma theta is a congruent subgroup of level 2, which is generated by generator S, T square and S, which I will talk about later. And the basic property of this new Hecke operator, which we donated as TPF, F stands for fermionic, is that it can map the Neville-Schwarz characters of fermionic rational CFT to the Neville-Schwarz characters of another fermionic rational CFT. And it also multiples the central charge C and the Neville-Schwarz widths. But here it can modulo half integer. And for those who already know fermionic rational CFTs, so our new Hecke operator TPF can also apply to other characters called NS tilde characters and R characters of fermionic rational CFTs. So one of our finding for this fermionic Hecke operator is that we found that almost all supersymmetric rational CFT, which was classified recently, can be realized as fermionic Hecke images of some very simple fermionic series, such as the supersymmetric minimal models. Okay, so this is a basic summary and the ideas of these Hecke operators. Is there any questions so far? Okay, okay, I'll go on. P is an arbitrary positive integer. It's a parameter in the Hecke operator, P. Yeah, I'll talk about it later. Yes. I think we talked before. So your rational CFTs are CFTs with a module space, but all CFTs I talk about here without module space. So I don't know yet how to apply this to your CFTs. Even in my rational CFT cases, there are also equal to supersymmetric case. But I think it's different from your rational SFT. Yes, but yeah, we can discuss this later. Okay, thanks. Right, so some very basics of 2D rational CFTs. So in these rational cases, the Hilbert space are decomposed into a finite sum of irreducible representations of the Carroll algebras. They're also the anti-Carroll part. And each characters are defined for each representation of the Carrel algebra, defined by this trace, by this real solid generator, and with the overall factor depending on the central charge. And Q is related to this familiar tau parameter on the Poincare upper half plane. And these characters are related to the torus partition function of the rational CFTs by this subsequent linear form. So in this form, so in rational CFTs, all these sets are finite, and we are familiar with many typical examples of 2D rational CFTs, including this Solomon models, West-Middle-Witten models, coset CFTs, monster CFTs, which only has one character here. And to be more precise, so the characters of 2D rational CFTs have this kind of Fourier expansion. So it has this overall factor depending on the central charge, C, and the conformal weight, HI. And all the Fourier coefficients should be non-negative integers. And in particular, for the vacuum character, the leading Fourier coefficient should be 1, which means the unique vacuum. And the subleading Fourier coefficients M1 for the vacuum character called the spin 1 current. So for West-Middle-Witten models, so this is the dimension of the Lie algebra. And importantly, these characters have good modular properties. So there is a very important quantity called the conductor of the theory, which is the least common denominator of this overall factor. This N conductor will be used in the plays an important role in the modularity of characters, and will be used in the definition of Harvey and Wu's Hecke operator. So so let's say more detail about the modularity of the characters of 2D rational CFTs. So first of all characters together form a vector valued modular form of SL2Z and weight 0. This means that there is this d-dimensional representation of SL2Z to GLD, which is there are d number of characters of 2D rational CFT. And for each element in the SL2Z, you have this kind of general transformation for the vector valued modular forms. And this is the nature of vector valued modular forms. But on the other hand, each character itself is also a scalar valued modular forms on a congruent subgroup of S2Z of level N. So we will donate this congruent subgroup of SL2Z by gamma N. Remember, this N is the conductor of the theory. So this means that the characters, we have two ways to look at them. So together they are SL2Z vector valued modular forms. So itself is a gamma N scalar valued modular forms. So to define Hecke operator, so Hecke operators are well known in modular forms. So for example, this is the original definition of the Hecke operator. So this was the first proposed for weight K scalar valued modular forms. So if we act TP, the original Hecke operator TP on a scalar valued modular form of weight K, so this is the definition. And from this definition, you can prove that TPF is still weight K SL2Z scalar valued modular forms. So there are many kinds of generalizations of Hecke operators to say Jacobi forms, and even as I mentioned, mathematicians also considered this Hecke operator on vector valued modular forms. But it turns out the most proper generalization to rational CFT characters, which are, as I mentioned, weight zero vector valued modular forms of SL2Z, was given by Harvey and Wu. So this Hecke operator should keeps both the vector valued modular form nature and the gamma n scalar valued modular form nature. So so here, as Harvey and Wu defined, so in this case, the TP, the P should be co-prime to the conductor N. And we donated this P bar as a multiplicative inverse of P modulo N, which means that P bar times P equal to 1 modulo N. And this Hecke operator TP is defined by very similar with the original definition, but there is you see that this definition depends on the conductor N and this P, and importantly, there is this transfer matrix, so which is called which is a representation of this rho P. So this rho P, as was found by Harvey and Wu, can be computed by the S and T matrix of the original vector value model form. So in this way, and here T and S are the traditional two generators of SL2Z. So by this very delicate definition, Harvey and Wu proved some very nice properties of this Hecke operator. So the basic property, so the basic property they found, of course, is that it always maps vector valued modular forms of weight 0 with conductor N to another vector valued modular forms of weight 0 and conductor N. Besides that, so they also show that this Hecke operator can map the central charge by multiple P and conformal weights by multiple P and modulo Z. And other phenomena they noticed is that this Hecke operator does not necessarily map a vacuum character to another vacuum character. So this means that vacuum character and non-vacuum characters can mix with each other. And this important transfer matrix rho sigma P is depending on the quadratic residue of P modulo N. So it has some very nice number theoretical interpretation. And more importantly, this Hecke image, the TP, the resulting vector modular forms has T and S matrix related to the pre-image by this very simple, in this very simple way. So basically, the resulting S vector value modular form has S matrix, which is this rho sigma P matrix times the previous S matrix. And they also found that pairs of Hecke images can found some C equals 8K holomorphic CFTs. So this kind of holomorphic CFTs means that this CFT has one single characters. Right. Yeah. Is there any questions about this definition of Harvey-Wu's Hecke operator? Okay. Yeah, that's a very good question. So in our paper, we even defined this so-called generalized Hecke operator. So first of all, this Hecke operator does not make sense when P is not coprime N, because here you will have some problem. So if P is not coprime N, then you will have tau plus some. The point is that this should be a fractional number. Okay. No, but if P is not coprime N, then this part is integer, and this does not make sense. So the definition will give you fractional. It's no longer a Q series, but a fractional Q series. Okay. Right, but in our paper, we even defined this generalized Hecke operator to allow this P sometimes can be not coprime to N, but that's very delicate, and we do not find a clear definition like this. We have some substitute conditions to establish a generalized Hecke relation, but we do not have an operator like this. Sorry, you said the Jacobi forms. I think it's different. Yes, because as far as I know, I also thought about this. I think this definition does not work for Jacobi forms. Only works for vector value model forms. Right. Let's look at one very interesting example. So this is the Li-Yang model, which is a non-unitary to the rational CFT. So the original Li-Yang model has a central charge minus 22/5 and 2 conformal weights. So there is 0 and minus 1/5. And the 2 characters are just the 2 well-known Rogers-Lambnugin equations in number theory, which has very good properties and many equivalent expressions. And so it's very convenient here to introduce the notion of effective theory of non-unitary minimal models. This effective description was also well known in the 1990s. That it is for non-unitary minimal models, sometimes we can exchange the label of vacuum and non-vacuum conformal primaries. That is to simultaneously adjust the central charge and conformal width such that the characters does not change, but you change the labeling of vacuum and non-vacuum. For example, here the effective description of minimal model have central charge 2/5, and then the conformal widths are changed to the effective conformal width 0 and 1/5. I'm sorry, this should be 0. And then the characters are the same. So the basic idea is to keep the conformal width plus minus central charge over 4 remains the same. Then this then we can say that the vacuum character of the original minimal model becomes the non-vacuum character of the effective Li-Yang model. Similar for the another character. And so for effective Liang model, we as I said, the scenario charge is 2/5, and the two characters are still these two, and they have this modular transformation of this S matrix and this T matrix as a vector value model form of weight 0. And we now want to apply the Hecke operator on this vector value model forms. And so this was Harvey Wu did in several years ago. So they found this very nice Hecke operator that is a connection that is somehow previously people didn't find this connection. So what they found is if you apply T7 Hecke operator on the Liang characters, you will get the two characters of G2 level 1 WEW model. So if you apply the T13 Hecke operator on Liang characters, which are the Rogers-Lamanutin equations I showed, Rogers-Lamanutin functions I showed, you will get F4 level 1 WEW model, the two characters. And further, so in this case, the conductor, as you can see here, so the conductor is 60, right? So you use this 60 in the definition of Hecke operator, and you just apply any TP with P co-prime to 60. You can find the resulting vector value model forms. You can compare that with the known characters of G2 level 1, 4 level 1. You found that they are identical. So these are some good Hecke relations found by Harvey Wu. And notably, if you apply T19 on this Liang model, you will get the very exotic theory, which is called the E7.5 at level 1 theory. This theory was found by Masamuki Sun in 1990s in the classification of 2D rational CFTs with two characters. So these are the few good examples found by Harvey Wu for the Liang case. So what I want to tell you here is that we have this some very good byproduct of Hecke operator. So it seems for the last more than 30 years, people didn't know how to define the Wessel-Minowita models for E7.5 for level higher than K. So previously, the only one known is this level 1 case. So I'm happy to say that from last year and this year, we made some very interesting progress on this, such that we can have the WEW models for E7.5 at a higher level. So to explain you this, I would like to take a detour to the E7.5. So this is an so-called intermediate Lie algebra. This was independently found by physicists and mathematicians. So physicists is what I mentioned, the Masamuki Sun's paper in 1988, and also found by mathematicians independently in representation series by Deligne, Cohen, and Deman. So both in 1996. So this algebra is not simple or semi-simple, but it behaves like a simple Lie algebra in many ways. So it has dimension 190 and dual cosine 94, and it filling a hole in the Deligne-Cvetanovich exceptional series between E7 and E8. So it is some sort of intermediate algebra between E7 and E8. So let me tell you how physicists found this E7.5. So in 1990s, modular linear differential equations were proposed by Iguchi and Oguri to classify 2D rational CFTs with a given number of characters. So the simplest case is consider the two-character case. In this case, one can consider the so-called second-order holomorphic MLDE, also called the Kaneko-Lagia equations, was studied also a lot by number series. So what Masamuki Sen found is that to require the solution chi as the characters of 2D rational CFTs, then this coefficient mu can only take a finite number, many discrete values. So here this D is the Serre derivative, which maps a weight k modular form to a weight of 2k plus 2 modular form. And this E2k is the Eisenstein series of weight 2k as 0. And we will require the two characters have this this kind of form where there is a unique vacuum, and and all these Fourier equations should be non-negative integers. These conditions, by these conditions, Masamuki Sen, they determine that there are only 10 possibilities. So these are the table I cut from Masamuki Sen's paper. You can see that except the first one, which is the Li-Yang model I just mentioned, then all other 8 cases are the level 1 WAW models with Lie algebra as in the Deligne-Tsvetanovich exceptional series. And then they have this question mark here. So this one, they noticed that it has a central charge 38/5, and the non-vacuum conformal weight 4/5, and the dimension is 190. And clearly, yeah, they couldn't find a simple or semi-simple Lie algebra here. So they give a question mark. But they commented that you can see that this is also a cut from their paper. So they discussed this m equals 190 rule. And they found that it seems this case, the characters also satisfy all the good properties. And they said that it does seems quite plausible that there exists a rational CFT corresponding to this rule based on some yet undiscovered symmetry algebra. So nowadays we know that this symmetry algebra is just E7.5, and this CFT is the WAW model of E7.5 at level 1. In fact, it is due to the effective Li-Yang model with respect to the E8 level 1, which means that it can be realized as a coset of E8 level 1 over effective Li-Yang model. So yeah, I also want to tell you how mathematicians found this E7.5. So this work goes back to the Deligne's work in 1996, where he found that this series of very special simple Lie algebras, they have some remarkable properties in representation series, among which one property is that the dimensions of some representations of these simple Lie algebras have uniform formulas. That means that for example, dimensions can be expressed as a rational function of the dual Cox number. And similarly, a lot of so theta here is the highest root. So many representations can be, the dimension can be written as a rational function of dual Cox numbers. And but these two mathematicians, Cohen and Daman, by explicit computations, they found 25 such kind of formulas. And later, Landsberg, Manive, they even proved a formula for arbitrary k theta representations. K theta is the highest weight of such representation. And in all these these formulas are now called the Deligne dimension formulas. They notice that if you put a dual cosine 24 there, they always give integer dimensions. For example, if you put a dual cosine number 24 here, you will get 190. You put here, you got this integer. but if you put any other Ducal number there, you won't get integer always. So this makes mathematicians also realize that there exists this intermediate Lie algebra between E7 and E8. So you can define it as a subalgebra of E8, while containing E7 as a subalgebra, and his joint representation can be decomposed as E7 representations. This is a joint. This is the fundamental representation of E7. So you can also realize that this algebra has a fundamental representation, which is 57. Okay, so this is some basic profile of this intermediate Lie algebra E7.5. In many senses, it is unique. And the question is how to define the WEW model for E7.5 for higher level. It seems for the last more than 3 decades, people don't know how to define this. And in our paper last year, we systematically studied this Hecke operators. We computed hundreds of examples. So that is, we act this TP on many 2D rational CFTs with a small number of characters. And among which we found many interesting examples, but among which the most interesting one is we found that if we apply this T19 on this minimal model M13,2, then surprisingly, the resulting vector value model forms seems to can describe the E7.5 at the level 2. So first of all, this T19 maps the central charge of effective minimal model M13,2. M13,2 has central charge 10/13, and you multiply by 19, you get this number, which turns out to be required by the E7.5 at level 2 central charge. These are the conformal widths by the Hecke operator give this. And the explicit computation, we just act T19 on this M13,2 characters. We will get this vector value model form. And we found many evidence that these 6 characters indeed should describe the Wessel-Zumino-Witten model of E7 at level 2. For example, all the free equations are integers, and you can see this spin 1 current is 190. And all these numbers are indeed the representations predicted by Cohen-Damans dimension formulas, if you put the dual quotient number 24 there. And also it has the correct central charge and conformal width. If you assume the previous central charge and conformal width formula for Wessel-Witten model still holds. Right. So this is a very good bonus for us to study this Hecke operator. And so this year we continued the study on E7.5, and we even found some coset constructions of E7.5 at level 2. So for example, we found actually 2 cosets. So these are this cosets is related to the so-called D6, A12 non-diagonal modular environments of M13,10. And these are very similar with the previously known so-called Maverick cosets found in 90s. For example, for E7, you can have this kind of coset. So this is actually a very big surprise for the VOA mathematicians. It's E7.5 level 2. So in this year we even studied the E7.5 at arbitrary level k, and very surprisingly we found that so for simple Lie algebra case, arbitrary integral level k will give you a rational CFT, but for E7.5 we found that only for level 1, 2, 3, 4, 5, you will have you will have a rational CFT, but for level higher than 5, that CFT cannot be rational. So this is also a very surprising finding for E7.5. Right. Any questions? So the E7.5 part finished. Is there any question for this E7.5? Yes, so this was constructed by mathematicians Landsberg and Manive. So they constructed this algebra using the sextonions. So it's between the quaternion and the octonion. So by that construction, they were able to derive this, they got some irreducible representations of this algebra. So our study recently is to construct this VOAs associated with E7.5. The Lie algebra itself was constructed by Landsberg and Manive. Okay. Okay, thank you. Right, so let's have a look at another example, which is the EC model. So this case, there are 3 characters. So with central charge half and common weight 0, 1/16, and half. So 3 characters are well known like this. And the conductor is 48, as you can recognize from this prefactor. And also S matrix for this vector value model form is also well known like this. So if you apply the Hecke operators on this EC model, so you will get this kind of tables. So so these are the Hecke operator T1, T3, T5, and what we found is we can realize this Hecke images as this WDW model characters. So for example, you can have many Hecke images can be interpreted as this WDW model characters, and here you can even find some very complicated WDW model. And even here, this is the so-called characters of baby monster view A. And you can find that the pairs of these Hecke images will give you the holomorphic C=24 as CFTs in the Schelikens list. So these are the number in the Schelikens list. And in fact, here we already considered the so-called generalized Hecke image, where we allow this this TP, the P is multiple of 3. So, but I don't plan to discuss more this generalized Hecke, because we still don't have explicit formula to define this. We have some conditions to define this generalized Hecke relation, but we don't have explicit formula to define generalized Hecke operator. Right. Now let's go to the fermionic case. So in this case, because there are fermions, so there exists 4 possible combinations of the boundary conditions along the 2 cycles of the torus. So so these are denoted as by combinations of Navier-Schwarz and Raman boundary condition. And these 4 sectors are traditionally called NS tilde R and R tilde sector. And for each sector, you can have a torus partition function. And each partition function, the fermionic partition function, can also be decomposed into the fermionic characters. For example, the NS sector, you will have NS characters, this sort of thing. And these NS characters, these 4 sectors under T and S transformations was well known to have this kind of transformation. That means under T transformation, NS and NS tilde sector will exchange, while the R and R tilde sector does not remains itself to itself. And under S transformation, the S characters will go to itself, but S tilde and R characters are exchanged. Well, the R tilde characters does not talk with the other three characters. And in the end, the four partition functions are the summation of four fermionic partition functions. So the four partition functions is the underlying bosonic partition function, which is still modular environment under SL2Z. And so it was analysis by my previous chaos colleagues that each sector itself is actually a vector valued model form of congruent subgroup of level 2. So for example, the NS characters is a vector valued model form of gamma theta. So gamma theta is defined in this way. So it's a congruent subgroup of level 2. So similarly, S tilde and R characters are vector valued model form of this gamma 0, 2, and this gamma 0, 2 in the a different gamma 0, 2. These three are all level 2 congruent subgroup of SL2Z. And so as you can see that, in fact, this gamma theta subgroup is generated by the S and T squared generator of SL2Z. Right, so this means, this is just to say that the NS characters of fermionic rational CFTs is a weight 0 vector valued model form of gamma theta. Okay, so more explicitly, so the fermionic characters have this kind of Fourier expansion. So you can see that here still overall you have this central charge over 24 and this Neville-Schwarz conformal weights. And but for fermionic characters, there will be it's not a Q series, but the Q2 half series. And the Raman characters is still a Q series. And all these coefficients should be non-negative integers still. And there are some special case of fermionic rational CFTs, that is supersymmetric rational CFTs. It is known that for supersymmetric rational CFTs, which means the bosonic degree and fermionic degrees are balanced, then the R characters will, for supersymmetric rational CFTs, will be constant. Right, so these are some, for example, some supersymmetric rational CFT known in 1980s. It's the n equals 1 supersymmetric Mio model. The central charge is defined in this way. These are the fermionic conformal weights. So if R and S difference even, then it gives the Neville-Schwarz sector odd. It gives you the R sector conformal weights, and these are the fermionic characters. This was all given well studied in 1980s, and if this P prime equal to P plus 2, then this supersymmetric Mio model is unitary. Right, and another good example of fermionic rational CFT is this A1 at level 4K plus 2. So it is known that this series have K plus 1 number of S tilde and R characters, and also K number of R tilde characters. And in the case of K equals 1, that is A1 level 6, it is well known that this series can become supersymmetric. Only for this K equals 1 case, it can be supersymmetric. And this is the well-known relation between the bosonic characters and the fermionic characters. So we can just think them as reorganization of the bosonic characters, such that all the characters satisfy the required properties for the fermionic characters. And in this case, for example, as I mentioned, the R2 characters will just become the constant 2. In fact, this is a consequence of Macdonald identity for A1. Right. Okay. So in fact, this supersymmetric, the fermionic addition of WW models when they have supersymmetry is a very popular question these days, and was studied, in fact, approved by Johnson Fried in 19. To get the full classification, and right, and in fact, our recent finding is that almost all known WW models with emergent supersymmetry so can be realized as fermionic Hecke images. So actually, in fact, there is only one we couldn't find the fermionic Hecke interpretation. Right, so now let's give you the definition of our new fermionic Hecke operator. So this Hecke operator is very similar with Harvey and Wu's Hecke operator. So it acts on the NS characters of fermionic CFTs to the NS characters of another fermionic rational CFTs, and the only change here is that the transfer matrix, the rho sigma p, is defined by only using T-square generator and the S generator. Yeah, because in fermionic in this S sector, so it only goes to itself under T-square generator of SL2Z. So this comes from the definition of gamma theta congruent subgroup of level 2. So interestingly, this combination is it turns out to be an inverse function proposed very recently, just last year by some Korean colleagues in the study of super modular tensor category. And we also can generalize this definition to the other sectors of fermionic rational CFT. Right, and some basic property we can show for this new or fermionic Hecke operator is that it maps the central charge C still to PC, and maps the Neville-Schwarz width to the P times the Neville-Schwarz width, but modulo half, and also the T matrix and S matrix is you can have a very similar relation between the pre-image and the image under this fermionic Hecke operator, and we also found that two fermionic Hecke images can often pair together as a holomorphic SCFT. So as I mentioned in the bosonic case, they will form C equals 8K holomorphic CFT. So here, for fermionic case, they can form a holomorphic SCFT with central charge is equal to 12K. And for example, in the C equal 12 case, this is the holomorphic means that there is one single Neville-Schwarz character. So for example, very famous C equal 12 holomorphic SCFT called Conway holomorphic SCFT. It has this kind of single NS character, And we do find many pairs of fermionic Hecke images can give this SQL12 holomorphic SFT. So let's just go to a simple example, which is the non-unitary supersymmetric minimal model. Supersymmetric, also called the supersymmetric Li-Yang model. This is supersymmetric minimal model 8,2. So which has this central charge and this conformal weights. This NS weights. In this case, we can also have the effective description as the bosonic case. So the effective theory, which we donate as supersymmetric Li-Yang level 1, it has central charge 3/4 and effective non-vacuum S weights 1/4. So you probably heard that this supersymmetrical model, it was known in 1990s that it can be realized as a formalization of bosonic minimal model M8,3. And the two Neville-Schwarz characters are just like this. And so the S matrix and the T square matrix are like this. So under the gamma theta modular transformation. So if we apply our fermionic Hecke operator on this supersymmetric mu model, so just by our definition, we will have some very interesting Hecke image, fermionic Hecke image. For example, if we apply, so in this case, the conductor can be seen here is 32. So if we apply T3 fermionic Hecke operator here, we found that this exactly gives the fermionic characters of A1 level 6, which I just showed you is actually a supersymmetric rational CFT. And if we apply T13 here, we will get this C6 level 1. So this is also a supersymmetric rational CFT appear in Jocelyn Fraser's list. And together, in fact, these two fermionic Hecke images will form this C12 Conway SCFT. Right. Yes, so in fact, we found we computed the fermionic Hecke operator on many fermionic series. For example, this is all the fermionic Hecke relations we found. And in fact, for example, here, this is one free fermion, and these are the fermionization of a lot of series. These are some supersymmetric minimal model. And so these are the fermionic Hecke operator. So this means that if we, for example, if we apply this T19 on this supersymmetric minimal model and 5,3, we can get the fermionization of E7 level 2. Yeah, so all these fermionic Hecke relations are new. And in fact, on this side, it almost covers the recent list of the classification of supersymmetric rational CFTs. So and this table. Okay, so in the end, yes. Right. So this is my last page. Okay, so just a summary. So we studied this Hecke operator of Harvey and Wu for many bosonic rational CFTs with up to 7 characters. And we developed the theory of WDW model of E7.5 for level higher than 1. And we also defined this fermionic Hecke operator on the characters of fermionic rational CFTs. We studied this fermionic Hecke relations with up to 5 Neville-Schwarz characters. And we also found that almost all known supersymmetrical rational CFTs can be realized as some fermionic Hecke images of some simple fermionic series. Okay, that's all. Thank you. I think yeah, hi, thanks for the question. I think the CFTs you mentioned are those CFTs with module space. I feel they are more complicated than the rational CFT I discussed here. Yes, is it known the characters of this CFTs it constructed, the characters? Oh, yeah, then I should look at them. I see. Yeah, thanks. Right. I think here the only property I know is this just the if right. So this Harvey Wu's Hecke operator if right if P and Q are both co-prime to a conductor N, then TP times TQ equal to TQ times TP. This is the property I know. I don't know or I don't know anyone has considered the algebraic properties of Harvey Wu's TP. Yeah, I think there may be some undiscovered algebraic property. Yes. Right. Yeah. Do I understand your question? Is does the pairs of Hecke images gives all Schelikens list? Okay. So the answer is no. So I think we in our paper last year we found that not all SQL24 homomorphic CFTs in Schelikens list can be covered as a pair of Hecke images. Yeah, yes. So I think our finding only covers part of them, maybe more than half of in their list. Yes. Yeah, probably. Yeah, they'll get visa next week. Yeah, thanks for asking. Thank you.